Hi, I'm Sang-Kil Cha from Carnegie Mellon. We are presenting our paper, Unleashing Mayhem on Binary Code. This work is joint work with my awesome colleague, Thanasis Evgerinos, Alexander Ribert, and my advisor, David Bromley. In this paper, we address automatic exploit generation challenge. This challenge is to automatically find bugs and generate exploits from a given program as an input. There are two parts, of course, in this challenge. One is to find bugs. In order to do that, we have to explore a program. For instance, suppose we have a GhostScript source code here. This program has a bug, and it starts from the main function, where we take a command line argument from the user input. This command line input is parsed using a while loop and switch case statement. And then if user input switch is not known, then we will try to output the error message using the outprintf function. Now, in outprintf function, there is a vsprintf function, which will essentially take user input and then copy the value to the buffer. And as some of you already noticed, this is a common buffer overflow condition if the user input is bigger than the size of the buffer. So the question is, how can we find this bug? Since this program has lots of cases, switch case statement, and if then else statement, we need to consider multiple paths. So this is the first part of the challenge. And the second part of the challenge is to generate exploit. What I mean by generating exploit is to transfer program control to attacker's logic. So for instance, from the previous example, we have a buffer overflow condition at vsprintf. If we look at the stack diagram of this function, then it looks like as follows, where the ESP pointer, stack pointer, points to the bottom of the stack, and we have several local variables and return address. And of course, when a buffer overflow happens, then it will override local variables and return address. And now, when the function tries to return to the main function, then we'll try to read ESP stack pointer, which is already overwritten by user input. So in this case, since instruction pointer will change by the user can actually hijack the control of this program. So these are the two parts of the AEG challenge. In this talk, we introduce Mayhem, a system to handle this AEG challenge for executables. What I mean by executable here is that we do not require to have a source code. Instead, we take raw binary as an input, I find and generate exploit. So I'll show you a live demo right now. So I have a VM here. Okay, so I have a VM here which runs Linux Debian 32-bit operating system, and I already downloaded the source code from the website. This is a GhostScript. This is a buggy line of code where the vsprintf is here. Now I already compiled down this source code into this GS file, and if I look at this is 32-bit executable. And this is a stripped binary, which means we do not require to have any debugging information. This is totally stripped binary. Now, if I just run this is a normal GhostScript program. Now I'm going to input this program to our system Mayhem. And Mayhem will take this program as an input and try to find and generate exploit. Now, after a few seconds, Mayhem will try to find a bug, and it will generate exploit. Now, if I look at the directory, there are several directories generated by Mayhem, and one of the directory actually contains our exploit. So let me show you here. So this directory contains the concrete input in order to replay this exploit. So this argv1 is the first argument that we need to provide and try to replay the exploit. So if I look at the content of this file, this contains of shellcode and several no-op sled and several random values here. Now I'm going to try to input this file using command line to the original GS executable. I'm sorry. Okay. Now, suddenly we have a shell. So what's just happened here is that Mayhem takes in a binary and then find and generate an exploit automatically. So this is the vision of Mayhem. We want to take in a raw input, a raw executable as a binary and try to find and generate exploit. So how does this system work? Well, first of all, in order to find bugs, we use symbolic execution. Symbolic execution takes in user input as a symbol. So at the beginning, the variable x can be anything. Instead of having concrete values, since we don't have concrete value for the variable x, whenever we hit conditionals, we have to reason about this formula. So in this case, suppose we take a path here, represented as red line, then we constrain the symbol x to be greater than 42. And for the next branch, we constrain variable x to not to be the same as max integer, and so on and so forth. Of course, if we take a different path, then we assert a different path condition to the formula. Now, throughout this talk, I'm going to call this path condition to be path predicate pi. Now, during the symbolic exploration, Mayhem will detect bug when it sees safety policy violation. In Mayhem, safety policy is very simple. Since we are doing binary-only analysis, our safety policy is also in instruction pointer level. Our safety policy is if instruction pointer is affected by user input, then we call it as safety policy violation. For the previous example, when we have a buffer overflow, after the return instruction, instruction pointer will point to the user input, which means in our case, the safety policy violation, and Mayhem will detect it as a bug at this point. After Mayhem finds a bug, Mayhem will try to automatically generate exploit by adding exploit predicate, which encode attacker's logic into a formula. For instance, can we position attacker's code to a certain memory address? Can we transfer control to attacker's code? By encoding this formula in conjunction with the path predicate pi, and by solving this formula, we can actually generate exploit automatically. Now that we know how we can use symbolic execution to find and generate exploit, are we all done here? Well, actually, when we try this AEG challenge on binary level, we had several problems. So in this talk, I'm going to mainly focus on two problems that we had during our design. First is efficient resource management. The second is symbolic index problem. For both of the challenge, we proposed two new techniques. One is hybrid execution, and the other is index-based memory model. So in the rest of the talk, I'm going to mainly talk about two challenges and the solution to those challenges. The first challenge is resource management issue in symbolic execution. Current symbolic execution falls into two categories. One is offline, the other is online. And both of these symbolic execution tries to manage resource in symbolic execution in different ways. First of all, offline execution tries to run a single path at a time. In other words, we generate a concrete input and execute a single path. And when we try to explore other path, we generate a new input and rerun the entire program from the scratch. By rerunning a program from the scratch, we only need to consider a single path, single program state at a time. So this is very memory efficient. However, we have in this offline execution, we have to re-execute the same prefix for every exploration. In other words, this is not efficient. There's another category of symbolic execution, which is called online execution. Online execution tries to fork executors whenever it hits a symbolic branch. Since we fork executors, we can explore multiple paths very efficiently without re-executing the same prefix. However, since we are using forking mechanism, we have memory issue, and we may hit resource cap. So there are two solutions. One, do not fork whenever we hit the resource cap. Of course, if we do not fork, we may miss several paths because simply because we cannot explore that path without executor. The other solution is fork, but when we fork, we take an entire snapshot of the process and then resume the execution using the disk. The problem here is that snapshotting entire program state can be very huge, and it requires huge I/O operation. So we propose a new technique called hybrid execution. The idea is first we execute in an online manner until we hit the resource cap. In other words, we fork executors during the exploration, but when we hit the resource cap, we do not suspend entire program state into a disk. Instead, we use path predicate to recreate the state. So the main idea here is that we can use path predicate as a succinct state representation, which allows you to suspend and resume the symbolic execution. And we call this lightweight information as checkpoint. And by using this checkpoint, we actually can reduce the program state from 9.4 megabyte to 500K. In other words, if we just take a snapshot of the entire program, it costs us to have 9.4 megabyte for the previous example Ghost script. But if we use our checkpoint mechanism, then we can reduce it to 500K. So hybrid execution allows us to manage number of executors in memory within resource cap, and it minimizes duplicated work because we are trying to avoid executing the same prefixes. And hybrid execution has lightweight checkpoints, which enables us to suspend and resume the symbolic execution. Now I'm going to talk about the second challenge. The second challenge is symbolic index. What I mean by symbolic index is that if user input is used as an index to access the memory, then we call it as a symbolic index. So in this case, variable x is symbolic, which means it is from user input, and it is used to access the memory as a memory index. So this is the symbolic index. And the problem here is that if symbolic index is used, and if we want to reason about the loaded value after the symbolic memory access, then we have to essentially reason about all possible cases that this symbolic index can refer to. For instance, in the worst case, we have to reason about 2 to the 32 all possible memory cells in the 32-bit machine. So why does this symbolic index matter in exploit generation? Well, there are many causes for this. One of the examples is that overwritten pointers. Suppose we have a C program where we dereference pointer and then return. Here, local pointer PTR points to a valid memory object. However, suppose we have overflow, buffer overflow before the memory dereference. In that case, user input will override not only the return address, but also it will override the local pointer PTR, which means it will mangle the pointer. Now, after the overflow, if we try to dereference the pointer, then even though we successfully override the return address, since memory dereference will happen before the return instruction, the program will be crashed even before the return instruction is executed. The second example of symbolic index is table lookups using symbolic input as table index. What I mean here is that table lookups is really frequent in standard APIs. For instance, if user gives user input as an argument to those functions such as scanf, vf, printf, then inside this function, we will use user input as a memory index, and we will use that index to look up a table. In other words, this symbolic index problem is a very frequent problem in symbolic execution, and it's a very general problem. So there are two existing mechanisms to handle this symbolic indexes. One is concretization, where we simply concretize a symbolic index into a single concrete value. And as you can see, of course, if we do this concretization, the formula, path formula, will be very small, and it's easy to solve. However, since we can see only single value after the concretization, we may fail to generate an exploit correctly. And in fact, 40% of our exploit was not successful if we do a simple concretization. Now, the second approach to the symbolic index is fully symbolically reason about all possible values. What I mean here is that if variable x is symbolic, then we represent all possible memory values into an array of all possible memory values into a formula. Now, as you can see, the formula is very big, and it is really hard to solve. However, if you can solve this, we can generate an exploit. So our observation to this symbolic index problem is that if we use path predicate to constrain the range of symbolic memory access, then we can actually reduce the size of the symbolic memory range. For instance, if you consider this symbolic execution tree where symbolic memory access happen at the end of the tree, then by looking at the path predicate pi, we can actually know that the range of memory x, symbolic index x, can have the value between 42 and 50. Now, taking advantage of this observation, and by using the symbolic execution state, we use a two-step approach to handle this symbolic index. The first step is resolve the bound and refine the bound into smaller range. And the second step is to construct the loaded memory value into a search tree. More specifically, in the first step, we find a bound of the memory index using a path predicate pi. So there are two steps. First, we use value set analysis to approximate the representation of memory index. Then we query solver to refine the bounds into a smaller range. And after we refine the memory range, we construct binary search tree, which we call it as index search tree, for all possible memory values. For instance, if index is reduced to have value from 1 to 4, then in this case, we can actually construct all possible memory values into a binary search tree, where the key of the binary search tree is memory index, and the leaf node of the binary search tree is memory values. And we can actually construct this binary search tree using if-then-else statement. And the intuition here is that if we use binary search construction for representing memory value, then we can actually associate memory index with memory values. And in fact, index-based memory model helped a lot in exploit generation. In one of our examples, without index-based memory model, we could not generate exploit in time. In other words, we had timeout. However, if we use index-based memory model, we could generate exploit in less than 200 seconds. The next optimization that we did is called a piecewise linear approximation. The high-level idea of this optimization is that we can represent actual memory values into a set of linear functions. So in the previous example, we can actually represent memory values into two different linear functions. Then by reducing the size of the formula using this linear function, we can actually speed up our exploit generation by twice faster. Now, in the rest of the talk, I'm going to talk about our exploit generation result. Mayhem generated 29 different exploits for 29 different applications. Among them, 7 was Windows, and 22 of them was Linux. And in fact, we found 2 unknown bugs. One was free radius, and the other was GNU goal. We report this problem to the developers. Now, I'll talk about some limitations of our system. We do not claim to find all exploitable bugs. And we do not guarantee, even though we have an exploitable bug, we do not guarantee we will always find an exploit. And of course, there are many rooms to improve symbolic execution and symbolic memory representation and exploit generation. And we also do not consider any OS defenses. If you are interested, please refer to one of the papers from our group, Q, which is represented in Usenix security. So in conclusion, Mayhem automatically find and generate 29 different exploits against Windows and Linux programs. We propose two techniques. One is hybrid execution, which allows us to efficiently manage resource for symbolic execution. The second technique that we propose is index-based memory model, which handles symbolic memory in real-world applications. I would like to thank you to our Shepherd and anonymous reviewers and our friends Maverick Wu and Spencer Whiteman. If you have questions, I would be happy to answer. Thank you.